See it.
I clicked it.
Let me see it.
It says end stream.
This is what people see when they first click into the video.
Hello. Hello. All right. Sorry for the delays. We had some technical difficulties. All right. Let's quiet down. Okay. So this is part 2 of Introduction to Deep Learning. So let's give a raise of hands of how many of y'all were here last time. Okay, it's fine if you weren't. I'm gonna just recap some of the stuff we covered last time at the start. Okay. All right. So this is gonna be kind of an overview of what we're doing again. It's the same thing as the last time. This is gonna be presentation, maybe a small little group workshop again, and then presentation again, and then Q&A at the end. Okay, so to review what we did last time, we talked about weighted functions. Anyone want to remind us what a weighted function is? Just raise your hand. Go ahead.
You got different attributes, and each attribute. It's basically when you got different attributes, and each attribute has its own weight corresponding to how much it influences a certain function or a certain value, kind of.
Yeah, that's correct. So it's trying to influence the output. So yeah, you got it right. So weight is basically how much this thing matters to the output. All right, any questions on what a weighted function is? I know I'm kind of speeding through it. Anyone have a question about weighted functions? All right, I'm gonna just recap. So this is the house price. So we went through a house price example where the house price was the weighted average of age and size, where we put a weight depending on how important the age is. Is it a positive thing for the price or a negative thing? And then same thing with size. Is it a positive thing for the house price or is it negative? So if you expect something that's 10,000 square feet to be good for the house price, it's probably gonna be positive. And if the age is a very good thing for the house price, it's probably gonna be positive. But if it isn't, it's negative. So that's kind of the idea of how weights kind of control how some things matter to the house price in this case. All right, so last time we were talking about how we got to pick these different weights and we call them parameters because they kind of mean the same thing. So last time we had y'all kind of randomly choose different weights and parameters to try to approximate this example. And here's a GIF of me trying to do that. And we can see how I'm trying to make the error close to as low as possible because error is kind of means it's not working as it's supposed to. I have no clue what that noise is, sorry. All right, so we can see that I kind of eyeballed it and tried to get the weights to be kind of similar to what I wanted. And basically meaning I wanted the error to be small. So a reminder what error is the idea of performing on a task, how wrong you are on performing a task. So if I'm trying to estimate the house price, it would be how far away I am from the correct house price, and that would be the error. And just to remind y'all, we found that the error was not supposed to be negative because having negative error is not really, it doesn't really make sense because you can't be negative wrong. I just mean you're right. So that's why we kind of had to make the error positive by doing absolute value, which just means you turn it to positive, or squaring it. And here's that idea laid out here. So we started off with the idea of differences, because when you're eyeballing it, you're trying to compare the two and seeing how different they are. So you're minusing them. And then here, where I mentioned that error doesn't make sense, if it's negative, you put an absolute value, and if you want it to be like more error when there's bigger differences, that's when you use the square. All right, that was just like a recap of what we did last time. So in case you weren't here last time. And I left it off at a cliffhanger where we were about to get to how to automate picking these parameters, because that's kind of like the magic of deep learning and neural networks. Like that's how we can get models that have like 20 billion parameters, because we don't have to manually pick these parameters. Otherwise, it won't happen. So that's kind of this thing we're going to be covering today is like the main like bread and butter of deep learning that makes it hard and like difficult for most people. And that is picking the parameters. So let me just start it off by leaving it where we were last time, where we basically, I'm gonna use a marker, where we basically had a simple equation and we were trying to get the weights, which is the parameters. So I'm gonna just write it down. So this is a weighted function, but with one x. So looking at this, think of a way to use like some form of simple algebra to like put this in terms of getting the weights. So what I mean is try to manipulate this equation so it's in terms of weight. So anyone have an idea on how to do this? Raise your hand. What do you say? You want to come up and write it? Yes. Yeah, weight on one side and everything else on the other.
Just divide by x. So yeah, y over x equals weight.
Right, so this is like something we all covered in probably high school. It's algebra. So you divide both sides by x, and then on one side you have y over x. This is called the inverse, and it equals the weight. So this is how we can get the weights. So in this scenario, like if we had I'm guessing most of y'all probably threw it away, but if we had our old papers, we could do this and we would get like basically perfect weights for those equations. But when we are talking about deep learning, we don't usually see this happening. There's a reason for that. And that is because the architecture or the function I showed you before last time, that's kind of a simple function. And I'm going to be talking about some of the limitations of it.
Sure.
Okay. All right. So this is how you would do it. So you would just, on one side, you have the normal equation. On the other, you're kind of dividing on both sides. This is called, when it's 1 over, I think this one's kind of reversed. That's a mistake on my part. But that would be taking the inverse, okay? All right, so I tried this out, and this notation is kind of a vector, and what it means is that it's basically equivalent to something like this. So when we're taking the weights here, this vector is the x, and this weight is like another vector. So it's equivalent to this, kind of what we did last time. And this is, we're just multiplying the two. So here we divide it on the other side, and then we get the weights by dividing 14,000 by 15, getting the first weight, and then 14,000 by 3,000, getting the second weight. So that's kind of what we would have done last time to get the optimal weights for that function. And this is simple algebra. So when you add in more examples, because in my example last time, it was just one example, we would have to make it into matrices, and there we take a pseudo inverse, which is just some fancy linear algebra stuff. But that's kind of the idea of what's happening here to get these weights. Any questions? Go ahead. So this is so in this idea, you can kind of make this vector. You can make this into a vector since this is the shape of 1 by 1. You can make it into 1 by 2. So that's kind of the idea if you divide it by a scalar number by a vector. So the idea would be you kind of just make this the same size as the other one, and then you just divide the two. So that's kind of what's happening there. If y'all didn't hear what he said, he was basically saying, how can you divide this number by a vector? And we basically just expand it out and then divide that. So that's kind of what's happening there. Any questions? I think you raised your hand.
I don't really get the notation here, like the vector, the matrix thing. I don't really get what it is.
Okay, so yeah, sorry, go ahead.
Compared to like the last example where we had like the grades and the house prices.
Yeah.
Like how would those how those would transform to that?
Yeah, so here is basically what's happening. We have this weight vector, which is getting multiplied here by x1 and x2. So that's kind of how it's translating over.
And x1 and x2 are the weights.
The weight is w, and x1 and x2 are the inputs.
And they're having the same weights.
And here, if we expand the weights out, it would be this. So here, w is a vector.
So you're really taking the dot product.
Yeah, that's basically it. So before we had a linear function, which just means we were multiplying it and then adding it up. And here, we're just using vectors because you have more examples and more weights. So that's the only difference. It's basically the same thing as last time, but we're making it into a vector because there's more different weights than just one. Any questions about that? Okay. So yeah, that was an example of how you kind of do that math and you come to like some weights, just to show you how you would have done it previously. And now I'll go more into kind of the limitations of the model I showed you last time, which was just a weighted linear average, which means you just multiply it by a number and then add it up. So here at the top, we have some linear examples. You can see something in common. I want one of y'all to point out what's in common in the top row. Yeah, they're all basically lines. And that's basically what linear means. It means it's a line. It's a straight line. That's what it means. And then on the bottom, what do we have in common? Yeah, they're non-linear, meaning that they don't have to be a straight line. They can be curved. They can be slightly increase in slope. Yeah, that's basically what non-linear means. And at the top, we have linear. So in the previous example, we were using examples that would have had like some form of linear computation. I know computation is a big word, but I just mean multiplying and adding. And in the bottom one, we have more like realistic stuff where things don't always get fitted by a straight line. So for example, we have compound interest where it increases over time, and population growth, which exponentially increases, and Newton's law of gravitation and like drug concentration. So these are some real life examples that we cannot like simply do with a linear average. So then I'm just trying to show some of the limitations of the previous system and try to do that visually. Any questions about that? All right, cool. So just reiterating the point where you can't fit to this data as good as you can with like a curved line. So here we have a straight line trying to fit this data, and it's kind of having a hard time because it's straight, and this one's kind of curved, so it has an easier job moving it. So what we can do to basically change our old way of doing it, to be able to fit these more complex data points or like functions, is we can add in non-linearity, which just means non-straight lines. So stuff that isn't straight line. So you just multiply it by something that isn't a straight line. So the reasoning behind that is because when you multiply something that is a straight line times another straight line, it's going to stay a straight line. But when you multiply by something that isn't linear, it's going to turn into some other shape that can be more robust to different data points. Any questions? Don't worry if you don't get it completely right now. I'm going to show some images later on where you can clearly see this idea. So actually the next one is going to be like a example of how one of the functions I showed right here, it's called a ReLU activation. It stands for rectified linear units. It sounds very complicated, but it's very simple. It just means at 0, everything below 0 just stays 0, and everything above it just stays itself. So it's kind of, if you're all familiar with code, let me erase this. One sec. It would just be so it would be 0 if it's if x is smaller than 0, and it would be itself if it's bigger than 0. So that's basically what's happening here. And over here, it's just trying to squish all the outputs to be between 0 and 1. So that's kind of what's happening there. It's called the sigmoid function. So these names are just some common ways of adding non-linearity. Any questions about what non-linearity is and the concept of linear and nonlinear? Okay, cool. So just to show you how like you can adjust a ReLU function to kind of fit different datas. And the source link from the YouTube video is down below. So you're just adjusting the function's weights and biases, which just means the y-intercept is the bias. And here I'm showing how you can use a ReLU function or a ReLU activation, like how I showed over here, to kind of like match a non-linear like shape. So before we could only use straight lines. Here I'm showing you how we can use this to approximate something that's not straight. So if you can't see too clearly, what's happening here is there's like a straight line, and then it's stopping, and then another one's added. So each of these is like the different weights we had before, but with the activation on top of it. And the activation is the ReLU thing that I was talking about. So activation is like, sounds very complex, but it just means doing this on top of the previous thing we were doing, which was multiplying the weights times the input. You just put this on top of that. And when we add these different activations on top of each other, you can approximate more like complex functions or data points. All right, so it's like kind of the same thing. We're just trying to see side by side the difference. So on the right, we have the reloop trying to approximate this curved line, and on the left, we have a line trying to do the same. And here, the reasoning behind why this actually matters is because when you're trying to approximate and you get it this much wrong, it's not going to produce good results. So like, let's say you're trying to predict like what number was in the image. The number might not have like a straight line relationship between like the inputs and the hidden features. And in those cases, we would want to have some form of nonlinearity to be able to approximate those situations. All right, so last time we talked about how we had the error and it was absolute, which means that's going to be a positive value. So if we had a graph of it, it would look like this. So that was the absolute version of it. And then if we had the squared version, it would be a parabola, which is like that. And here I'm just showing that same idea where the error was the difference, either absolute or squared. And our goal is ideally to have as little error as possible, because that means our function is doing exactly what we want it to do. So now we'll be going into like how we can use these very complex architectures that can model complex data points or functions, and how we can kind of make it like find the weights. So if anyone's thinking, why don't we just use the what we did before, which was like divided by x, and we get weights? Why don't we just do that? So the reason why we can't do this anymore is because once we add some form of nonlinearity, this relationship doesn't hold anymore. And there's some very complex mathematical proofs for that, so I won't go into it. But that's kind of the idea of why you can't do this anymore, because the linear relationship just doesn't hold when you just divide it over. Okay. So how would we like try to make our way to the bottom? So since we can't really just get the weights just directly, like we did before, we're gonna have to try to move our weights into a direction where the error basically decreases. And we kind of go, and this is kind of what modern neural networks do today. This is the main idea of deep learning and neural networks. And that is where we slowly adjust our weights or parameters in a way that the error basically decreases. So if you think of GPT or ChatGPT, what it's doing is it's basically adjusting all its 12 billion weights, or however many billion, in a way such that on the task it's trained on, the error is as small as possible. So I'm going to be going through how you can kind of do that. And the first thing we need to think about is the slope. So when we have a diagram like this representing the loss, what we think about is we want to get over here all the way down to the bottom. How would we do that? Anyone have any ideas? Just raise your hand. Go ahead.
I mean, what I would say is, like it's saying, like shift like the x position to the left or right randomly. See if the error got bigger or larger. If it got bigger, do the opposite direction. If it got smaller, then keep going.
Yeah, that's kind of the idea. But you got an answer?
Well, generally speaking, I believe you want to take the gradient of this function and you want to go in the negative direction.
Yeah, so do you have an idea of why you would want to do that? Like, why that would work?
Well, I mean, you could represent the gradient as like geometrically as like the the dot product, and the multiplication of two magnitudes and the cosine of the angle between them, right?
Sure.
So if you wanted to say maximize it, that's only possible when they're perpendicular. And the gradient is perpendicular to, the tangent plane of the function. And so that would give you the maximum direction for increasing it. So naturally, if you wanted the smallest, you would just take the negative of that.
Yeah, I guess that works too. So, yeah, that was a good explanation. So the kind of the idea is kind of a combination of what you mentioned. I mean, you just went more in depth about it. So if you move upwards, you can kind of notice that the error is going down. And if you move downwards, you kind of notice that the error is going up, sorry. And when you move downwards, it's going down. So the idea is we can kind of get a direction of where to move the weights by taking the slope. So just to remind you of what the slope is, like imagine a straight line at this point, and the slope is the rise over run. So in this left case where our point is all at the left, if we take the slope, because it's going downwards at this point, it would be sloping downwards. That would mean that the slope would be like, let's say -2, right? So let's say the slope at that point is -2. Would you want to go in the direction of the slope or against the direction of the slope? Just raise your hand if you have an idea of what to do. So in this case, if we decrease the value of the weights, which is -2, if we go in the direction of the slope, it will be going up because we're making the weights go less. So if we go in the opposite direction of the weights, it would be moving this way. So in that sense, we would want to go in the opposite direction of the slope. So let's say we had a point on this side and a line here. And let's just say that the slope there was a +2. Which direction would we want to go in? The direction of the slope or the opposite direction? All right, yeah. So if we increase the weights, it would go up. So if we decrease the weights, it'll go down. And that's kind of the reasoning behind this idea. We would want to take the slope so we have a direction of where to move our weights that can decrease the error. So this idea is called gradient descent. It sounds very complicated, but the idea is very simple. You take the slope and you go in the opposite direction. So by saying the opposite direction, I mean you move the weights in the opposite direction of the slope. So you might also be thinking, now I know the direction, how much do I move? Now that's a good question. Whoever asked that, it was definitely not me. So let's say I move in the opposite direction and I go all the way here. This is not good. So I moved my weight from here to here. It was going the opposite direction. So let's say my thing, adding 2 here, moved it here. So anyone have an idea on how to kind of solve this issue? So we're moving too far. We're moving our weights too far. Anyone have any ideas on how to fix that? Go ahead.
I'm not sure if it's correct, but like have like the steps really big at the start and then make it smaller every successive step.
Yeah, that's a good idea. So that's actually what people do in a lot of these really complex optimization function. And that sounds complicated. It just means you try and decrease the error. That's what optimization means. But anyway, yeah, that's a good idea, and that is what you do. So you basically take steps in the direction you want, so you don't go too far. And that is called the learning rate. It's basically a limit on how far you go. So let's say I had -2. That means I have to go, like let's say I did 0.01. I might only go here instead of all the way here. That's basically what it's doing. It's limiting how far it changes. And just to give you another example to make this idea more clear, let's say my point was over here at the start, and the slope was -10. That's a big number. And if it was -10, and I decrease the value by like 10, let's say that, it might still go over here. So this is still an idea where it might still go a bit farther than it wants, but it can just do the same thing, but as long as the steps are small enough, it will eventually go down here. So that's the idea of like learning rates and like taking a step in the right direction. That's what gradient descent is. So anyone want to summarize what I basically just said, what gradient descent is? Just raise your hand. Go ahead.
Basically just going back and forth and trying to get the gradient as close to 0 as possible.
Yeah, so do you want to explain more like how you move it and how much you move it?
It's like you start out with very big increments, just going back and forth, where the slope is, I guess, starts either negative or positive, and just going kind of back and forth, and then steps slowly decrease over time until you get like really close to 0, I guess.
So that's close. In gradient descent specifically, we keep one single learning rate throughout the process. In more advanced versions, you can change them as you go along. But in gradient descent, you keep one step size. But the idea is you learn which direction to change your waves by knowing the slope. You go in the opposite direction. And you got an idea of how much you want to move by having like the size of the slope. So that's kind of the idea. You do want to limit the step amount because you might go too far, but you don't want it to be too small because then you might like just change it little by little, and it might take like forever. So that's kind of the idea of gradient descent. And just to clarify what gradient means the slope. So when it's descending, it's using the gradient, which is the slope. So whenever you think of gradient or derivatives in your mind, just think of slope. Okay? Go ahead.
Is there an optimal range for the learning rate?
Depends on the problem. Usually what people do is they just kind of empirically test it. What that means is they just test random different learning rates and they just kind of go with it, you know? So like if any of y'all heard about ChatGPT, what they did to train it was they tried a bunch of different parameters or different learning rates, and they kind of figured out this one tends to perform better. And that's kind of how people do it. There are some ways you can kind of automate the process of finding it, but that's a bit more complex for what we're trying to teach today. Okay. Any questions about? Okay, go ahead.
How do you deal with the local minimum?
The local minimum, what do you mean?
Like, what if there is a lower point further down the function?
So that's a good question. So he's asking basically, we want to go all the way to the bottom, right?
What if there is lower point?
Yeah. So what if there's a lower point? So in this case, let's say this is the shape, right? We just keep on bouncing around until we get to the bottom, right? So how do we deal with lower points? So there's different ways of how you can take steps. And in some ways, you might take a step where it keeps on increasing. Like if the slope is a lot higher, it would just kind of increase like a ball. You know, try to like get over that point. But generally speaking, it's just like how you take the steps. People change to kind of get over like these. I don't think I'm explaining that right. So let me show you how it looks like. So basically what he's talking about is like an idea where you have like this, where this is where we start off, and this is where you want to go. Because this is like the actual minimum. This is the local minimum. It's called the global minimum, and this is the local one. So what happens is some algorithms, this is a bit more advanced for right now, but some algorithms, they basically try to use momentum where they can kind of go over this and go to the global one. But generally for now, this is a bit advanced. But the idea is you'll find the local minimum, and hopefully that local minimum will be good enough. That's kind of the idea. So usually people do talk about this stuff, but that is more later on. But it's good that you're thinking about this stuff. Any other questions about what gradient descent is? Maybe some of the people in the back. Do y'all have an understanding of what it is? Okay, sure. All right, so here's like a graph of the loss. So just to remind you what the loss was, it's the error, but over many different examples averaged out. So what that means is if the first example I tried, it had an error of 0.40, and the next one I tried, it had an error of 0.1. I just averaged the two out, and that's the loss. So yeah, that's the loss. And let's say we graph our loss for different weight values. That's kind of what this graph is doing. So this is basically the average error on the examples it was trained on, and this is the value of the weights. So to bring back the idea of trying to use this to move the weight in the right direction, this is kind of what we'll be working with. We take the slope at the point where it starts. Like let's say the weight was 2 when we started off the algorithm. We take the slope of it at that point, and we have a direction of where to move now. So that's kind of what's happening here. Just to go more in depth of how this works, because this is the loss at the end of the day, we want to know how to change the weights. So just to write it out, or like to show you visually what's happening, or like how this works is, I'm gonna erase all of this. Is the purple marker visible? Okay. The live stream is on there, so it's kind of bad if they can't see anything. Okay, so let's have a visual example of how like kind of the multiplication was happening with the neural network. So let's say these are the different weights. They're represented as circles, and these are the inputs, which are the x's. So these are the different weights, and you're multiplying them too when they're here. And then let's say there's an output, which is just the weighted average of these, and that will be the y. I'm just trying to visually show what's happening when we are getting to the loss. So we take the y, and then let's just call this a square, because it's not the same thing, it's not a weight. And we call that a loss, or I'll call that an error function, because that's more accurate. Error. So we take this, and then the correct one, we'll call that the label. So that is the correct value, and we're trying to see the difference between the two, like I said before. So as you can see, this is kind of the value. And when we're graphing this out, we're having only the final error value being graphed. So there's a bunch of things in between. These are weights. So there's like a bunch of things in between the error and the actual weights. So if we just take the slope at this point, how do we know how much to change, let's say this way? So that's kind of the problem we have to solve. And this idea is like very core to neural networks. So let's just see if anyone has an idea of what to do. Anyone have an idea? Okay, cool. All right, so let's think about it a little. So let's say this is the slope of the full thing, and this is like the last part of it, right? What we might want to do is break these apart into small little components and just find the slope of each. So we can take these and multiply them with their respective slopes. So that might sound a bit abstract when I just say it out loud. So let me just write out the stuff. So dy minus label here, and let's say it's squared. And that is the error. And here is, just say x times y here. And this is the activation. Oh wait, I guess this wasn't completely accurate. You'll take the max of it, remember the activation. So that would be like kind of over here. So usually how this happens is like one part of the neuron does the weight multiplication, the next does the activation. So we call this A. And this is the A. I think I might have confused some of y'all. Just ask questions if you're confused about this. Just raise your hand. Did I lost anyone here or lose anyone here? Okay, so let me just explain it again. So first step we do here is we multiply x3 times, this should be 3, weight 3, right? This is the first half of the neuron. The second half is applying that non-linearity to make it able to model more complex things. So what we do is we take this output, let's say it's A for some reason, and we feed it through the non-linearity, which is 0 and then A. Can you see this?
Yeah,
Do you have an idea of what's happening now?
I have an idea about it. Like, I don't fully understand it, but it's wrong.
No. What's your like question about?
Like, I don't know what's changing, like, every single time with the W. Is A changing?
Okay, so let's see. Like changing every time what? Like
Every single, like, for the gradient descent.
okay, yeah. So what he's asking is every time we make a change to make the error lower, what's changing? So what we're trying to change is the weights because we're trying to find the perfect weights for our problem where the error is as small as possible. So just to bring it back to why we have weights to begin with is because weights like give us something to change that can change basically the output of the function. And we want the output of the function to be as close as the labels. So we use these weights to change what the function does. So that's why we change the weights rather than like some of these other values. Because the inputs is like the example, like let's say we input a picture and we want to get like the output of like what numbers in that picture. We're going to be changing the weights, not the examples. Because the example should always be like the same, or it should always be able to perform on those examples. Does that make sense?
That makes more sense.
Okay. Okay. So we multiply the weights and then we put it through some nonlinear function so it can be able to model more complex things. And that's kind of the three things that are happening here. So the idea of getting to the slope of each of these weights is by breaking them into their components and taking the derivative individually rather than combined. Because if you just try to take the derivative of this whole thing, it gets really hard. And it's like basically the only way to do it is to break it apart. So here's like a visual understanding of me breaking it apart. into its components. So first we have like the error function, which is like a parabola, which means it's like a U shape. And then we have our nonlinear function, which I showed before was a 0 and then straight. And at the end, we just have our linear function, which just means you're multiplying a number by its input. So these are kind of the three things. And when you look at it like this, it seems kind of simple how to get the derivatives. Here, I don't know how many of y'all are familiar with calculus. Raise your hand. Okay. So everyone's familiar with calculus. Okay, that's great. So in a parabolic function like this, let's say it was squared, you can just times it by 2 here, and that'll be the derivative or the slope. So that's kind of the idea of it. You take the slope of each of these little functions, and the last step is to multiply them together. So if you look at this here, I think the slope of this one is like 2. The slope of this one's like 2. The slope of this one's like 2. And if we multiply them together, I think that's like.
Actually, I think this looks one.
Oh, okay. Well, the idea is you multiply them together, and we'll get the slope at this point. So you break it apart, and then you have to multiply them together to get the full slope of the function. And this is called the chain rule, if y'all are familiar with this. It's where you break it apart and then you put it together. And the reason why it's useful in neural networks is because everything's already kind of composed in like little components. And since we have like different amount of weights, or we may have different like layers and like layers upon layers, we might only want to change this one and not this one for some reason. And we can kind of go backwards and calculate what each part is like doing. So here, like we get the derivative here, it's gonna be 2. And let's say we get a derivative here, it's like 1.5, like the activation, 1.5. And then here we get the derivative or the slope here, it's 4. Yeah, so we multiply these two together, and then all three of them. So I think in a case where this would be more easily shown is if we had like another unit here, and that one has a different one. So here it might be 7, and you can change these weights by multiplying these two, and then you can also change these by multiplying all 4 of them. So this is why we go backwards from the start, and instead of like starting from here and going all the way there, because we kind of repeat some computation. The idea, this idea is called back propagation. It's where you compute them in components and go backwards from the loss. Anyone have questions about that? I was really confused about this when I first learned about it. So just raise your hand if you have questions.
On this chart right here, is weight 2 the most optimum? Is what it's saying here.
So we're just saying that this is where like one of the weights started off at. So in this example, I made it very simple, just to like demonstrate the idea. And I think in this example, it's like just one weight. So that's why it's like this. So we started at weight 2, and the idea would be we change the weight values to lower the loss. And you just can break it apart into these 3 functions to get the slope. Okay. All right, this is called back propagation. Yep. So just to remind you of the idea, it's kind of where you go backwards from the loss and you compute the slopes or derivatives. So any questions about like chain rule and back propagation? I know you asked one. Go ahead.
It's those little weights, like are those little circles that are there like additional weights?
Yeah, so in this example, I'm just using them to show how when like using this idea of going backwards would be useful. So these are different weights. So the idea is they would both have these two things. Does that make sense?
She explained the last part.
All right, so these three are weights, and I put them here to demonstrate the idea of when going backwards would be useful. Because let's say these are weights I also want to change. So it would be useful to go from the back, from the error, all the way back to the first weights, because you save the amount you have to compute. Because if we just computed this one, and this one, you're gonna have to recompute all of this for these ones.
How would you like? So would you like add like those small weights to the big ones for each one, or like not?
So when you get the slopes of each of these functions, you multiply them together to get the full slope of this section, basically. Did that answer your question?
I mean, like going, for example, like the bottom, it's like I think that's weight.
This one? Side.
So the bottom weight is like weight 3.
Okay.
And then going to 7, like the weight is 7. It's like, how would you recompute it?
Okay, so how would I recompute it?
Yeah.
So let's say I took, let me make this clear. Let's say I had this big old function over here. It would just be yeah, okay. Let's just assume this one doesn't have an activation for some reason. To make it simpler, we call this weight 4, and then we'll call this weight 3 times x. Okay, and then we square it. So here, minus the label. So here, this is like pretty complex. And if we break it down to get to W3, we already take all of these things to get, already get the derivative of W4. Does that make sense?
So you take derivative of that whole thing.
Yeah, so what I'm saying is when you break it up into components, right? You break it up into these components. If you take it all just to get this one, you already computed all of these components already. And if there was another thing we need to change in the middle, we would have to recompute the whole thing just to get this one when we already computed it. So we basically go backwards and we compute the different weights backwards. So we can edit these weights also, and then right after that, we already know these derivatives, then we can edit this one.
All right, it's 8 o'clock.
All right, sorry, this one was running a bit long, probably because the door was locked, but hopefully next time we'll get to the workshop bit, but sorry about that. That's all for today. We gotta do our sign-in though. There's like an internship panel thing on Wednesday, October 11th, if y'all wanna go to that. And there's a QR code for free pizza. Sorry, go ahead. All right, and I'm gonna show the sign-in form real quick, sorry, for anyone. What's the number? All right, this is the sign-in form. The number is 8431, by the way, so sorry about that. 8431.
For the form, I'm not a freshman or a sophomore, but when I submit it, it says check if yes, and it won't let me submit without checking it.
Can you?
Just put yourself as a sophomore.
All right, and this is the last one, it's the feedback form. Sorry, what?
It asks for code.
Huh?
Oh,
It's 8413.
8413 is the code.
8413.
And if you want to give feedback, here's the form. 8413.
Oh, did I say it wrong?
Oh.
It's 8431. Sorry.
8431.
8431.
Okay.
I heard it.
What?
First link is just for